Hello and welcome to our webinar with the title Measuring Temperatures and Temperature Alarms with Thermal Imaging Cameras from MOBOTIX. My name is Thomas Gladl. I'm a member of the MOBOTIX trainings team and I will guide you through this webinar in the next roundabout 30 to 40 minutes. We want to talk today about the possibility how to measure temperatures with a MOBOTIX thermal camera. What are the limitations, systematic limitations coming from the physics, and what are the possibilities in order to receive a possible accurate alarm when a temperature is too high. This is what we want to discuss, and we want to discuss in detail the setup and what we need to configure in the MOBOTIX cameras. Before I start with the content itself, I want to inform you that we also record this webinar, and you will find this webinar again on eCampus. Yeah, this is our e-learning platform where you can play back a lot of webinars what we have already made, and you have the possibility to play it back whenever you want, so on demand. If you don't have an access to eCampus, just write us an email to ecampus@mobotix.com, and then you will receive your personal, free of charge account details where you can log into eCampus and see all the webinars what we have there. Here in the webinar, you can of course also ask questions. Please send us your question after the webinar by email, then we try to come back as soon as possible back to your question so that we can actually help you with whatever problem you have. So talking about the thermal camera and what we want to do here. So actually, let's get started with a first glance to the electromagnetic spectrum. And of course, with a thermal camera, we are working in a different wavelength than in the optical with optical cameras. Yeah, with optical cameras, we are using normally the spectrum between 390 nanometers to 770 nanometers. This is the visible range where we have the colors. Then we have this near-infrared range, what is up to 1000 nanometers. This is the range where we have the so-called near-infrared. Yeah, this is still the optical range. And here we can work with black and white cameras, because here these black and white cameras are sensitive for this part of the light, and here we can also work with this light with infrared illuminators. Yeah, so but all these things all these cameras are working in the optical range. Yeah, so this means here we are talking about light. And now when we talk about the thermal cameras, we are talking not about light. Here we are talking about heat radiation. Yeah, and this is what we measure actually with the thermal camera. We have in the MOBOTIX thermal camera a thermal sensor. This is a microbolometer, and this microbolometer is sensitive in the range 7.5 to 13.5 micrometers. Yeah, this is the mid-wave infrared range, and here we do not measure light. Here we measure heat. Yeah, and what the camera is doing is that it's converting this heat information into an image, and what we see is actually the heat transformed into a light information, what is like an image. Yeah, so this is what we see there. Yeah, so actually we talk about a different physics. Yeah, this is the physics of the heat, yeah, not of the light. Yeah, and therefore we have a little bit different behavior. We have a little bit different influences and physical laws, and this is what we need to talk about when we want to talk about accuracy and influences. Yeah, so let's come to the next part, and here we see the typical setup if we want to measure the temperature. Yeah, if we want to actually, what we do actually is that we measure the temperature with our camera, and to make it visible. And so we can say our camera is actually the measuring device. Yeah, this is on one hand, and on the other hand we have our object. Yeah, and if this is a human, this is our measurement object actually. And if we want to see this heat distribution in this object, then we measure him. Yeah, so these are these two things, and then we have, of course, some influences. Yeah, and the first influence what we have is this distance in between, the distance in between our object and our camera. Yeah, this is normally air. Yeah, this air has a certain temperature, has a certain humidity, yeah, and all these things will influence, of course, the values that are measured in this measuring device. Yeah, so this means that this measured distance is giving an influence actually to everything what we measure about the object. This is one fact. And the other fact is that we have, of course, also other sources, our other heat sources, like for example the sun, what we see here. The sun is also emitting heat. Yeah, and some of this heat what is emitted here, this will be reflected by the surface of the object. Yeah, and what we measure then is actually the reflection of this heat. It's not coming from the object itself, it's coming from this object and is reflected from here, and we can measure it here. Yeah, so this is also measured and influencing the value what we measure here. And then we have also another fact. So this was what we have talked about first, when the heat is transmitting a certain the air is transmitting through the air. Yeah, this is the transmission. Yeah, then we have talked about the reflection. Yeah, and then we have also a part of radiation what we also measure, and this part of the radiation is radiation what is going through our object. Yeah, so we have also some stray radiation. Yeah, so here this heating, and with this heating, of course, there is also some radiation what is transmitted through the body and what is also measured here with our measuring device. Yeah, so we have different influences. We have the influence from the distance, we have the influence from the reflection, and from the transmission from other stray radiations. And this is all together what we measure with our thermal camera. So this is our setup, this is a physical law. These are, let's say, the influences what we have to deal with if we want to talk about measurement and accuracy. Okay. So let's have a look now to the next page, and let's put it all together. We have on one hand our influence what is coming from the distance, what we have said here. Then we have the influence what is coming from the object and from the stray radiation. And then we have, of course, the influence what is coming from the measuring device itself. Yeah, so we have there a certain accuracy in our camera. Yeah, and this is what we need to have a look at now. And what I have here, this is the data sheet of our camera. Yeah, so we are using a thermal image sensor in two models of our cameras. This is the M16 and the S26. And we have then two different types of thermal sensors. One is the thermal, or it's called the thermal sensor, and then we have the thermal TR sensor. The TR sensor is the abbreviation for thermal radiation. Yeah, so this is a higher accurate sensor, and this is of course also a sensor what has a higher accuracy if it's about the absolute value of the measurement. Yeah, and what we see here, what is in the original data sheets, what you can see there, we have for the thermal sensor, for the standard thermal sensor, plus minus 20 degrees Celsius, or you can also say Kelvin, because it's only a different offset. Yeah, so but with the thermal radiator, we have an even higher accuracy of plus minus 10 degrees Celsius or Kelvin. Yeah, so this is something what we have in our data sheet. But meanwhile, since we have the MX6 cameras and since we have higher, or let's say better sensors also in these cameras, we can say that since we have the MX6 generation cameras, we have new thermal sensors with higher accuracy, and this means that the standard sensors have an accuracy of plus minus 10 degrees Kelvin, and the thermal radiator has even an accuracy of 5 plus minus 5 degrees Kelvin or Celsius. Yeah, so this is something what is first of all important, that we have a very high accuracy for the thermal sensor, what is plus minus 5 degrees Kelvin, yeah, for this TR sensor. So this is something what we need to keep in mind, and then let's have a look onto the other influences. And of course, when I've talked about these influences from the distance, yeah, and also from the transmission, yeah, we can do some configuration in the camera, and therefore we have some settings. Yeah, so we have the emission of our object, we have the transmission, and we have actually, this is unfortunately in German, but this is our ambient temperature. Yeah, so these are the values what we have to set up there. I will show you this in a minute live in the configuration of the camera, and there we have, of course, then also the English dialogue. Yeah, but actually the values are the same. So we have from the object emission the value, from the transmission of our distance the value, and the temperature of our ambient temperature actually. So, and this is what, these are values where we can do some settings in order to calibrate these influences. Yeah, so here we have some possibilities to do this. And of course, we have influences coming from the distance, and this is of course also caused by some effects. So if you look at the weather conditions, for example, yeah, we have of course in some circumstances rain. Yeah, this is also then attenuating our signal. And here we need to distinguish between light and heavy rain. But if we are talking about fog, yeah, then we have, of course, a lot of little water drops in the air, yeah, and this is attenuating very much the signal. Yeah, so this means the more the fog, the less is the signal. So this is a big influence. Yeah, and but what we can see is that actually also fog is penetrated. If it's light fog, yeah, so also the heat radiation can go through this fog. Yeah, so even if maybe we do not see with our optical sensor something, the thermal imaging sensor can see something. Yeah, and this is what I can show you here. So here I have an example. Yeah, so I had here this a smoke generator, and I was creating some smoke. Yeah, and what we can see here with the visible, with the optical sensor, that from a certain amount on, we cannot see the object anymore. But here on the right side, and this is side by side, thermal and optical, on the right side, we do not see any effect. Yeah, so although we have a lot of smoke, this is not affecting our image. Yeah, and on the left side, we cannot see the object anymore, yeah, due to the smoke, but on the right side, we can see the object. Yeah, so this is actually because of this thermal sensor technology. Yeah, so this is a big advantage in all the cases where we have to deal with fog, yeah, or light fog and smoke. We can work with thermal, and we can penetrate then this effect. Here I have an example what is very similar. Yeah, on the left side, the optical sensor, on the right side, the thermal sensor. Also, we cannot see the object here, we can see him here. Yeah, and of course, if he's coming closer, then we can also see him on the optical side. Yeah, but this is just to show you how we can look through smoke. Okay, so now let's talk about the influence what is coming from the distance. Yeah, so the influence what we have seen before was the influence what was coming from weather, or from actually from the medium actually. Yeah, so what is the air, yeah, and the humidity in the air, and maybe also from smoke, some other particles. And now let's talk about the distance itself. Yeah, and here we have made some tests, because here we wanted to see what is the effect actually, yeah, if we do measurements in different distances. And therefore we have used something what is called a black body radiator. Yeah, this black body radiator gives the opportunity to set up a certain temperature, yeah, and this temperature is then highly accurate. Yeah, so if you set this device to 50 degrees, it's keeping this 50 degrees, yeah, and it's also calibrated, so it's very accurate, it's very constant, yeah, so, and we can be sure that this temperature is always existing there in this black hole, what we see here. Yeah, and actually the temperature is there then 50 degrees. Yeah, and this black body means in the physics that this is an ideal body. Yeah, so this means this can radiate. Actually, this can emit all its energy, all its warmth energy in 100 or per 100%. Yeah, and this is the definition of a black body radiator. Yeah, so this means all the energy is emitted, and we measure 50 degrees directly at this device. So, and now we have made different measurements. Yeah, we have a measurement made in 10 meters. Yeah, here you can see this device. And in 10 meters, we had already a lower temperature. This was only 48 degrees Celsius. Yeah, and then we have done some other measurements. Yeah, so in 20 meters, it was 44, in 30 meters, 43, in 40 meters, 42. Yeah, so what you can see is that with the distance, also this influence is getting bigger. The bigger the distance, the bigger is the influence. Yeah, so this is something what we need to keep in mind, that this is also an influence what is affecting our measurement number. Okay. Then let's come to the next one. Yeah, so the emissivity of the object. Yeah, so when I've talked about this black body radiation, yeah, I've said that this is the ideal concept of a body what is emitting all its energy. Yeah, so here we say the substitute of the ideal scenario is a black body with an emissivity of 1, yeah, equivalent to 100%. Yeah, so however, real objects do not emit all its energy. Yeah, so and this is depending on different things. Yeah, this is one thing is of course the material. Yeah, what kind of material is this? What is the surface? How many and what layers are on the surface? How rough is the surface? And then how do we look at the surface? From what angle? Yeah, and the degree of polarization, yeah, of this radiation. Yeah, so these are all effects what are affecting the absolute value of our measurement. Yeah, and what we see here in the next table is that we have some emissivity values for different materials. Yeah, we can see aluminum, anodized black, 0.95. So you can say nearly 100%. Yeah, but the same material polished, 0.05. Yeah, so you can say equivalent to around about 0. Yeah, so this means the same material, but the surface is different. Yeah, and this makes a big difference here. Yeah, and this is also for a lot of other materials the case. Yeah, so this depends how is the surface and what is actually the material. What kind of material do we have here? Yeah, so you can see asphalt, for example, 0.97. Yeah, copper can be 0.8. Yeah, or nearly nothing. Yeah, and paper has a very high emissivity. Yeah, so here we have different values. And of course, we need also, if we want to measure the temperature of a body, of the surface of a body, we also need to know the emissivity of the body, of the skin. Yeah, this is also something what is affecting our measurement value at the end. And yeah, talking about skin temperature, of course, we need to also consider how is the temperature distribution in the human body. Yeah, so you cannot see it here with this image of the human body, what is also made with the thermal imager. Yeah, so the core of our body, this is actually having this core temperature. Yeah, but on the skin we have a different temperature. The skin temperature is between, and this is something what I found in Wikipedia, what is between 33.5 and 36.9. Yeah, and here, of course, the skin temperature is different. Yeah, if you look to the core or if you look to the head. Yeah, so this means what we measure is actually the skin temperature, and the skin temperature on the head, what is anyway not as hot as the body. Yeah, so this means here we have to expect lower temperatures, lower normal temperatures. Yeah, this is actually the case. So we have two effects again. Yeah, one is that we are working with the skin, that we have a lower temperature at the skin, first effect. And second effect is that if we measure on the head, we have a lower temperature than on the complete, on the body, on the core of the body itself. Yeah, so you know if it's about fever measurement, you know exactly that fever measurement devices, there you measure in the core of the body. Yeah, you never measure somewhere else, always in the core of the body. This is the reason, because there it's most accurate. Yeah, and of course the surface and of course the head is much cooler, and it's not really giving a real feedback what is the actual body temperature. Okay, so this is one effect, and of course also if you look to the core body temperature and if you compare this to your body, yeah, so we have a table here where we see the forehead, yeah, is cooler than the core body. Yeah, and if the core body is like we see here in the table 36, yeah, you can say the forehead is 2 degrees lower. Yeah, this is not linear. Yeah, so this is going a little bit with the higher the temperature, the less is the difference here. What you can see also here in the graph. Yeah, but actually you can say that the forehead is lower than the body temperature. Yeah, so you cannot really say. If the body temperature is high, that you have also the same temperature on the forehead. Also, yeah, most time if the temperature is too high, also the head is because there you are sweating. Yeah, there you actually emit your energy. Yeah, and this is then also getting hot. Yeah, but just to repeat it, yeah, the head is the coolest part of the body, or a cooler part of the body, and of course the skin as well. So let's talk again about the influences. And of course we have our physics, yeah, we have our physical laws, and the physics is describing it in formulas. Yeah, we don't want to go into the deepness of these formulas, but just to make it to make a summary here, we have on one hand we have our emission. Yeah, so this is this here, the emission, what is emitted from the body, what is received from the measuring device. Yeah, this is the emission. Then we have the transmission. Yeah, so if the energy is going through through something, then we have this transmission value, and this transmission value we have as well for the radiation what is going through the body. Yeah, so we have transmission here and we have transmission also here. So, and we have actually the reflection, yeah, the reflection what is here. Yeah, so, and we have tau for the transmission, epsilon for the emission, and rho for the reflection. Yeah, so this means if you, and we have talked about this before, if you take this all together, all these influences, yeah, you can say all these influences are commonly all the influences what we have to deal with. Yeah, so we can say all the influences are altogether 100%. Yeah, and this is what we actually do in the physics, that we say transmission, emission, and reflection all together, everything added together is all our radiation, is all what we measure, is everything is 100% equals 1. So far about this background, yeah, this physical background, but let's also have a look to the overall measurement influence what we have. Yeah, so we have said that we have different influences. We have, of course, our influence of the camera. Yeah, and if I look back into this table, what we have seen here, this was our table. Here we have said we have the accuracy here of plus minus 5 degrees Kelvin. Yeah, and this is of course also what we have then here, plus minus 5 degrees Celsius or Kelvin. It's similar, it's the same. Yeah, it's just a different offset. This is actually the same value. Then we have the influence of the distance. Yeah, and if you remember to these different measurements, what we have done in the different distances, yeah, you could see that we have up to 10 meters that we have had roundabout plus minus or roundabout 2 degrees difference. Yeah, so if we are talking now about this accuracy, and if we have a nearly ideal measuring setup, yeah, we should measure within this 10 meters, and then we can expect to have around about 2 degrees influence coming from this distance. Then we have our object. Yeah, our object, there we have the influence coming from the emission, actually, from the surface, from the skin, yeah, because our skin is not a black body radiator. Yeah, our skin has not 100% emission. Yeah, so also here we need to keep in mind that we have here some influences, and these are also coming from different skin colors, from different skin surfaces. Yeah, and here we have then these plus minus 3 degrees as well. And then we have the stray radiation. Yeah, so this means reflection, what is coming maybe from heating. Yeah, what is maybe coming from air condition, what is maybe coming from the sun, depends where you do your setting. Yeah, and this is also something what is going into our equation. Yeah, and if you now put everything together, yeah, if we are talking about the overall measurement, you can say, of course, everything together is our summary. Yeah, so and if we put everything together, you can say round about plus minus 10 or 12 degrees is actually the accuracy. Yeah, so this means if we think about measuring temperatures with the thermal imager, and this is not depending on different, that we don't have good quality or other things. This is just physical law. These are just limitations what are coming from the setup. We can say, if we make a round number, we have plus minus 10 degrees accuracy. Yeah, so this means we cannot really say that we can measure temperatures and that we can use this value to measure very low differences. Yeah, but, and this is now the task. Yeah, we want to get an alarm if there is a temperature too high. Yeah, so, and this is now the question: how can we still get a reliable temperature alarm? Yeah, and of course we also need to think about first from the side of our influences. And if you look again to the setup what we see here, if we have our measurement device, yeah, and if we have an object and a reference, yeah, and this is very, very important that we have a reference, but is very accurate, yeah, means that it's calibrated, that it has the right value, and it's constant, yeah, that it's not changing the temperature. And most of the times you have this with these black body radiators, that they are constant and very good calibrated. So if you compare these measurements now, then you can eliminate a lot of the influences. If you look back to this, to our equation, what we have here, our influence of the camera. Of course, yeah, this camera, it has a certain accuracy. Yeah, it's measuring here and it's measuring here. Yeah, but the same values are valid for both. Yeah, so this means if it's maybe plus 3, let's say it's plus 3 for this, and it's plus 3 for this. Yeah, so this means this can be eliminated. This is going out of our equation. Yeah, so this means if you compare these two things, yeah, then we don't have this problem with this influence anymore. So this is this accuracy of the camera. So let's talk about the influence of the distance. Yeah, it's the same here. If we have our reference and our object in the same distance, and if we measure in the same distance, yeah, this is also going out of our equation. Yeah, because it's the same influence actually, and therefore not affecting our measurement. And then the object, yeah, of course, this is now something what is actually affecting our measurement, because the skin is not a black body radiator, yeah, and therefore we have to do some settings, yeah, and I will show you how we can do this settings, what we can do in order to calibrate this, yeah, in order to compensate this value. And then the next thing is the stray radiation, yeah, and this is also the same thing, yeah. So both devices here we need to transmit through the same medium, yeah. So you can say this is actually something what is also going out of the equation, yeah. But of course, if we talk about transmission through the body, yeah, this is something what is of course different here and here, but this is also something what we need to compensate actually with our settings. Yeah, so but at the end, you can say, if you do a setup like this, that you compare two things, a lot of influences will disappear. Yeah, and this gives us the chance to, if we compare, to get a really high accuracy. Yeah, and this setup I want to show you now in real. Yeah, so let's get out of this presentation and let me show you here our camera. So let me first show you the setup. Yeah, so first of all, here you can see me in the camera. We have here an M16 camera, and this is an M16 TR. So on the right side, we have a thermal imager. On the left side, we have an optical sensor. And of course, with the optical sensor, you can see the optical image. Yeah, you have me. Here you can see my laptop. And what we see here, this is the black body radiator. Yeah, so this is a black body radiator. What I have set up to a temperature of, you can read it here. Of course, it's a multiplex signal, so therefore it's not constantly visible. Yeah, but the setting is that it has now 34 degrees. Yeah, 34.0 degrees. This is actually the temperature what we have in this black circle here. Yeah, so this is our temperature, what is there, very constant and very accurate. So, and on the right side, you can see the image of the thermal. Yeah, so you can see that we have here this, this higher temperature of 34 degrees. Yeah, so, and we have, you can see here that where we have here this display, it's a little bit more warm, so you can recognize this. We have, of course, the laptop, what is a little bit warmer, yeah, and me, what has also a certain body temperature. Yeah, so this is visible in this thermal camera, in this thermal imager. So now we need to see, yeah, first of all, how we can do our, yeah, our calibration. Yeah, how we can do the calibration so that it's fitting to our settings. And we do calibrate our sensor if we go into the setup menu. Yeah, when I open the setup menu, we have here the image control settings. And in the image control settings, we have the last entry, the last link here is the thermal sensor settings. Yeah, so here I want to open this thermal sensor settings. Yeah, hopefully you have also seen the other webinar what is about thermal cameras. Yeah, this other webinar is also something what we offer as a webinar where I explain all these different settings. Yeah, so I don't want to repeat this here. I just want to come to the important settings where we want to do now the calibration. Yeah, and this is with the TR sensor, of course, one thing, and this is linear mode. Yeah, linear mode is a very important setting. It must be activated in order to make a setting with every pixel of the sensor. Yeah, so what we can do with our thermal sensor is that every single pixel, yeah, and this is actually our complete sensor, every single pixel can be used to measure temperature. Yeah, and if we measure temperature, for example, in this field here, yeah, we measure every pixel, and what we can even see here, yeah, so you see this this crosshair symbol. This is hopping from point to point. It's always hopping to the hottest pixel in this field. Yeah, so we measure with every single pixel, and we show the highest temperature of the highest pixel here. Yeah, so, and this is actually only possible if you are in the linear mode. Yeah, so otherwise you cannot measure. So linear mode must be activated. So then we come to the configuration, and this is actually now our important part. This is temperature compensation. Yeah, and therefore we have to activate this manual configuration. Yeah, because otherwise it's taking everything with 100%. Yeah, but if we want to compensate our setting, if we want to compensate our influences, we need to activate this. Yeah, and then you have here three different values. Yeah, what we have seen already before in my presentation. Yeah, so this is the same dialog. Here we have the object emissivity. Yeah, so this is actually the emissivity of the object in %. And then we have the atmospheric transmission. This means the transmission of the air. Yeah, the transmission in the air of our medium. What is the air? And then we have the ambient temperature. Yeah, so and to do now a setting, let's maybe first do the setting. Let's maybe set back everything to the factory defaults. Yeah, it's coming when you come in the factory default. It's 100, 122. So let's do this, 100, 122. Yeah, so this means there is no compensation value. Yeah, so, but what we see here is that we have now, and of course, due to the fact that we have this black body radiator, what is very accurate, we can say, we know that on this place we have a temperature of, and this we can read here, 34.0 degrees. Yeah, so this is the temperature what we have in here. Yeah, so we need to calibrate now our sensor so that we have the 34 degrees. Yeah, so this is now the task. So we need to find the settings so that it's possible. So now we need to see how we can change this. Yeah, so this means if there is, if we say 100 here, yeah, this means this would be the ideal medium where our heat radiation is going through. Yeah, so this means if it's a lower percentage, it's less radiation what can be measured. Yeah, so this means the result must be higher, or if we correct this, if we change now the settings, the camera tries to put something on top to actually fit to the real value. Yeah, so if I say, for example, 80%, you will see it's now even rising. Yeah, so it's now showing 40. Yeah, so it's not helping here to make this percentage lower. But what we do is, if we say that we have a certain atmospheric effect, that we are using this, in this moment, 20%, and we are influencing this 20% with the value what we have below. Yeah, so this means, if I would say 100 again here, yeah, so this means we have a transmission of 100%, and the temperature does not have any effect at all. Yeah, so even if I say 10 here, and have a look here, we have now 36. Yeah, and if I say 10, it's not changing anything. Yeah, because we have here no part of the transmission what is influenced. Yeah, so if we want to have something what is influencing by the temperature, we need to say there is a certain value. Yeah, and therefore it makes sense to say, for example, and we have to find the values. Yeah, we have to set a value, and I try now with 90%. And just as a side information, our correct temperature what we have in here is 34. What we see currently is 36.6. So this means we see 2.6 more than it's actually there. Yeah, so this means when we talk about the accuracy, we have said plus minus 5. Yeah, we have now a plus value. So the camera is actually showing more than we have in the reality. So we need to compensate this, that it's getting lower. Yeah, so this means we also need to tell the camera there are some effects so that the camera is subtracting the value. Yeah, and of course, now if I say 90 and maybe, let's say again 22, let's see what happens. Then we have 38. If we now set up a higher temperature here, let's say instead of 22, let's say maybe 10. Oh, it's even getting higher. Why? Yeah, because of course the algorithm says the temperature is lower. Yeah, I need to add something so that it's getting in the right direction. Yeah, so this is the wrong direction. We need to set it higher. Yeah, so let's say 30. Yeah, then we have 37 here. Yeah, so and then we need to rise this until we have our 34. Yeah, and if we say 40, for example, coming to 36, and I've done this before, yeah, just to have a value what is nearly fitting, yeah, and I found that with 55, yeah, I have a calibration what is then fitting to our 34. Yeah, now you could say, okay, it's now 34.4, but you will also see that this number after the point will also change due to the self-calibration of the camera with the time. Yeah, so here this is also compensated, but we could say, let's say maybe 56. This is also, of course, also changing with the ambient temperature what I have here in the room. Yeah, this has meanwhile also changed. Maybe let's say 57, and then we should have a value what is fitting and what is compensating actually all these influences. Yeah, so let's say, okay, this is now a setting where we have done our compensation. But you could already see now that we have some effects. Yeah, if I have now a larger distance, if the room temperature changes, all these influences will also change our measurement. Yeah, so this means this can be right now for this setting. Yeah, but this can be completely different in 1 hour. Yeah, so here all what I have explained before, yeah, all our influences are counting into the equation. Yeah, and what we have talked about before, that we want to eliminate this, we can do if we now try to compare values. Yeah, and this is something what we can do with our cameras, because here, what you can see here, we have different windows. Yeah, so I have a window here and I have a window here. And I have done now the calibration, and if I walk now into this window, you can see the value what is measured. Yeah, this is now 34.6, yeah, .7. Yeah, this is the skin temperature in my on my head. So this is actually this is what we can measure in the moment. And what we want to do now is that we want to make this comparison in order to eliminate all these influences. And let's do this. We can do this, and therefore we have to go into the setup menu of our camera. And in the setup menu, we have to set up all our sensors. Yeah? And the sensors will be set up in the event overview. So I go into the event overview, and what we can see already here, of course I have prepared this. We have our environmental events. Yeah? And one is our temperature comparison. Yeah? And if I open this, you can see this is my temperature compare sensor. Yeah? And I have said, okay, I want to use the thermal radiometry, and I have my measurement area. Yeah? So this measurement area, what we have here, is actually the area what is in there in this rectangle here. Yeah? So this is actually the place, the area where I measure the temperature. So, and now I say I want to compare this with a reference temperature. Yeah? So I have here the possibility to say either absolute or reference. Yeah? And in order to make this comparison possible, I say reference. And then I can say the trigger mode. Is it each pixel? So every single pixel what is measuring? Or do we have a percentage over the whole window? No, I want to measure with every pixel. And then I have to set up in the next field here the reference area. And this is actually in my in my black body radiator. Yeah, so this is what I've done here in my black body radiator, that I've said, okay, this is my reference area. Yeah, and what I'm doing then is that I can say I want to have an alarm if my measurement area, what is here, what is this big one, if this is higher than this area here. Yeah, so this is exactly the thing where we compare. Yeah, so what is now eliminating a lot of influences. Yeah, so what we say here is that we say if the temperature here in this window is higher than our reference window, then we want to have an alarm. Yeah, and we can show this numbers, we can show the values. Yeah, this is what we do here, and we can here select what we want to, yeah, Celsius or Fahrenheit. And then we can say action type. Is it every single measurement what is creating this alarm, or maybe only the first one? Yeah, of course, if we have changing objects in the windows, we should have the possibility that every object is creating this alarm. Then show the measurement areas, so that we have the rectangle. Yeah, show the level temperature. This is the setting here. Yeah, also this coordinates is off. Yeah, this crosshairs. This is this hopping crosshair, what is always showing the hottest pixel. Yeah, and the profile name. This is the profile name. What I have set here, temperature compare. The other one, what we see here, this reference temperature is just for my reference window. In order, I have only used this to show the temperature in the reference window. This is the only reason why I have this. Yeah, I have set here a trigger level of 40, yeah, what I never reach. Yeah, but here we would have an alarm if this temperature would rise over 40. But this I have only done so that I can show you what is the temperature here. Yeah, this is just for this reason. So, and now we can use this. Yeah, and what I've done in the setting here of my camera is that I said, okay, if this comparison is triggering an alarm, I want to have a visual alarm. Yeah, and this is defined in the action group. Here in the visual alarm, you can say, or you can see what I've set up. Yeah, so here we have the temperature compare trigger. This is my reference comparison. Yeah, and if this is coming, then we have this alarm frame, this visual alarm actually. Yeah, and this is what we can see if the alarm is now coming up. So if I'm now coming into this window, you can see that now my temperature is higher than our reference temperature, and this means this comparison is positive, yeah, is triggering the alarm, and we get an alarm. Yeah, and this is actually very accurate, yeah, because we do just a comparison. We compare this with that. Yeah, so this means like this we eliminate a lot of influences and we can be highly accurate. Yeah, and this is actually the thing how we can work, because what I have told you in the beginning, yeah, with temperature measurement, it's very difficult due to the physics, due to all the influences, due to all these effects. But if you have the right setup, and for the setup you need to have a constant temperature reference. Yeah, so this must be a constant temperature, this must be an accurate temperature. And the best thing is to buy something like this, what is a black body radiator, because there you can set up the temperature, it's calibrated, you can be sure this has the right temperature. This should be in the same distance like the bodies you want to measure, yeah, and then you can do this comparison, and then you can have a trigger. Yeah, and for a practical setup, I would say that you let a lot of people go through where you are sure that they have that they are under the temperature level. Yeah, and then you can set up your calibration so that there is no alarm coming. And if the alarm is coming, then the temperature, or that the alarm is coming if the temperature is too high. Yeah, and like this, it's very accurate. Yeah, because even if the temperature in the room is changing, this effect is changing for both. Yeah, and therefore we don't have this effect. I think this was all what is important about this. I hope I could explain it in simple words so that it was understandable. I want to say thank you for watching, thank you for listening, and I am happy to see you again in another webinar. Thank you again, have a nice time, and stay healthy. Bye-bye.